Hi guys, this is problem 8 that we have been talking about a lot lately, and I am sure that many of you are still a little confused about what is it that they are requesting in this problem. So I thought it will be a good idea just to solve it in detail. So pay attention because the process is a little involved. So let me read it for you, please. The position of a Pinewood Derby car was observed at various times. The results are summarized in the following table. So they give you a position time table where you have the time measured in 1 second intervals from 0 to 5 seconds. And so your position is given after each second. So you can readily tell that after 1 second, the car has advanced 2.3 meters. After 2 seconds, the position is 9.2 meters. So that's 9.2 meters from the origin. Remember, that's the position, not the displacement in 1 second. After 3 seconds, the position is 20.7 meters and so on. So with that table, they request that you use this data to construct a smooth graph of position versus time. Now, if you are going to do position versus time, the horizontal axis is, of course, going to be the time measured in seconds. And then your position measured in meters is going to be on the vertical axis. Now you have to decide based on the space available and the values that you have, how many divisions in your grid are going to represent 1 second and how many meters you're going to represent in each division. For example, you have a nice wide space for the horizontal axis, so you can take quite a bit of room to mark each of the seconds. 1 second, 2 seconds, 3 seconds, 4, and 5. If you can see the grid there, you can see that we choose to take 1 second for 5 squares. So each of the little divisions in the grid is 0.2 seconds. On the other hand, you have to go up to 57.5, approximately 60 meters. So I advise that you use 10 meters as your standard division. And I'm going to use 2 squares in the grid for that. So we have 10, 20, 30, 40, 50, and 60 seconds, 60 meters, sorry, for your vertical axis. Now, of course, to construct the graph means to first plot the data. What do we mean by plot the data? You actually take each of the ordered pairs and you mark them with a dot. So your first dot is 0, 0. Second dot, 1, 2.3, which is about here. 2, 9.2, approximately here. 3, 20.7, approximately here. 4, 36.8, which is around this place. And finally, 5, 57.5. So that is approximately over here. So you can easily see from this series of dots that this graph is not going to be linear. Actually, if you want to look at it more accurately, you can take Desmos and you can see that, well, in this case, I have already put in the data here in the table to the left. And if I see the dots, well, they pretty much look like that, right? We all know this is supposed to be a parabola or a quadratic function because what this actually tells you is that your car is accelerating. So how then do we take this series of dots and we construct a smooth graph? Basically, you have to draw freehand, no ruler. You draw a curve that is as smooth as possible and that is trying to pass through all of the data available. Now, this, of course, depends a little on your drawing skills, but the whole point is, of course, that this is an approximation and you are going to have some rounding to make. It's not going to be accurate, but that's fine. It's not meant for you to get an accurate reading. It's supposed to be a statistical thing. So, this is the instruction that we have already fulfilled. We have used the data to construct a smooth graph of position versus time. That is part A. Part B is where things start to look a little disconcerting. In part B, they ask you to construct tangents to the x of t curve, finding the instantaneous velocity of the car at several instances. Well, what's the idea? Why do we need tangents? Remember that the whole point of this situation is that if you have a position time graph, that position time will give you the velocity if you have the slope. But wait a second, you don't have the slope for that. What we have is basically a graph that is a curve, and then using that curve, you can get lines that are tangent to the curve at many different points. For example, I can take this line and I can try to align it as much as possible with the curve. It's not going to be exact. That doesn't matter. All that you need is that this is more or less tangent to the graph that you have. Now, what's going to happen? What you're going to have then is 2 points that could be, for example, approximately here and the point of contact. And with those 2 points, you can get the slope of this line, which is a measure of the steepness of the green graph right at the point of contact. For example, the first point here is, of course, 1, 2.3, and the second point, remember, each little square is 0.2, so this is 2.8, comma, what is it? 10 meters. Therefore, when you calculate the slope for this red line, you're going to have 10 minus 2.3 over 2.8 minus 1, which is equal to 4.28. Now, the units for the numerator are meters, because that's a position time graph. The units for the denominator are seconds, so this is meters per second. What is this telling you? This is telling you that for this line, the slope is 4.28 meters per second, but that slope represents the velocity of the car. It's not the total velocity, it's not the average velocity, it is the velocity right at this time, right at 1 second. Therefore, what you're getting there is the instantaneous velocity for the car at t equals 1. So, get the idea? The whole point is you can do this as many times as you want. You can take this same line and you are going to have a tangent at time equals 2. At times equals 2, of course, you're going to have a larger slope. Then you can calculate a third one at time equals 3. Let's do it approximately over here. You can see that this is getting a little harder to do with each drawing because the graph is less and less of a curve as we move on. It's getting closer to a straight line for each time interval. But then the whole point is, of course, that what you're doing is an approximation. You're not doing an accurate thing. It doesn't have to be accurate at all. Now, in your case, you are going to need to do this with a ruler on paper. So try to keep your pencil well sharpened and try to read your distances very carefully in each of the drawing. So you can take, for example, these points for the second line, and then approximately say here, and you can take a couple of points for the third line like this, for example, and so on. So what we are going to do is eventually, once we have all of the pairs, is that we can calculate each slope, and each of those slopes is going to tell you the velocity at each particular instance. So let's go there. So these are the values that we can calculate from each of the lines, getting each of the slopes for 1 second, 2 seconds, 3 seconds, 4, and 5. Notice that conspicuously, we have avoided calculating anything for the first time, for 0 seconds. We want to show that this should reasonably be something close to 0 because we think that the car probably starts from rest. But in order to look at this graph, well, if it shows an accelerated motion, we would expect that this data lies approximately on a straight line. So first, let's look at it from a technological point of view. So I have a 0 here, and then the second one is 4.28, and the third one is 8.93. Next, 15.91, 18.33, and finally 23.08. Now, you can see that this is not quite perfect, but it certainly resembles a little bit what should look like a straight line. Maybe some suspect data is the one for time 3, which looks a little or way above what it should have. But the whole point is that these points are more or less on a straight line. And so if you try to do them by hand, let's go back to your problem, then you have a situation where the highest value is 23. So we might want to go from 0 and say 5 by 5. This is 5 meters per second, 10 meters per second, 15, 20, and 25. And remember, this is now a velocity versus time graph. So this is your velocity in meters per second. Now your time can be drawn with the same, exactly the same scale as the graph before. So you have 1, 2, 3, 4, and 5 seconds. And this is your time in seconds. Therefore, your first time is 1 second, and you have 4.28, which is approximately over here. Then 8.93, which is almost 9, approximately over here. For 3, you have 15.91. That's close to this. Then 18.33. So that's 5, 10, 15. 18 is about here. And 23.08. 5, 10, 15, 20, 23 is approximately here. And so, yes, it does look a little bit like a line. You might want to pick a line that you can draw, and you want to make it go as close as possible to all of the data that you have chosen. So in this case, we want to format this thing by giving it a red color and making it a lot thicker, because we want to be able to see it. And you can see that if you try to make it close as possible to as many points as it is reasonable to find, then it is very reasonable to say that the very first velocity that you have is actually 0. So that's going to be your answer for part D. This looks very much like the original velocity was 0. However, before we consider that, the first thing that we want to know is we want to determine the average acceleration of the car. And for that average acceleration, we have the slope of the velocity time graph. Now that slope can be obtained by just picking 2 points. For example, the coordinates of this point. This is 5.2 for time, and this is 25 for velocity. So this point is 5.2, 25. And then another one that will be nice will be, for example, this one. And in this case, this point is 2.6 for time, and this is exactly 12.5 for velocity. So this point is 2.6, 12.5. So you might want to remember, yes, you guessed it, the slope of the velocity time graph is going to give you the acceleration. So your acceleration is going to be 25 meters per second minus 12.5 meters per second divided by 5.2 seconds minus 2.6 seconds. And you take that to your calculator and you get 4.8 meters per second squared. So that will be a very good approximation for your average acceleration. Now, when they ask you what was the initial velocity of the car, you can simply reason it out like this. Since the VT graph passes very close to the origin, it is reasonable to say to state that the velocity at time equals 0 is 0. The car is starting from rest. Now, if you want to check because you think that this is not accurate, you can actually do that in Desmos. I'm not going to do it because we are already over time, but the actual mathematical process tells you that this is 4.6 meters per second squared. So your approximation of 4.8 actually looks very, very good. And well, if you remember how, it will be a very good idea to try and do that in Desmos. But then this is the process that they requested for the problem number 8. I advise you to finish your worksheet and hand it in as requested. Thank you for listening and watching, and I'll see you tomorrow.